Okay, part 3, movement. In this section, we're going to look at how we can use magnets and electromagnets to make things move, just like an electric go-kart. Okay, so here is the basic idea of why this whole system works. I have here two permanent magnets. So this is a piece of iron that I have made into magnets. And I've put into there a wire. So this red thing here is a wire. Now you should, what you can see is I've already drawn the magnetic field lines around this wire. So a little test, can you work out, is the current in this wire going into the page or out of the page? Well, we're going to use our right hand rule, and this time we have a wire, so I want my thumb to be the wire. My fingers need to represent the direction of the field. So I can see that the field's going that way, so I need to turn my hand so that my fingers are going in the right direction, and then I can see that my thumb is going into the page. So if I was to add this, I would put a dot to show that the current is going into the page, not out of it. Okay, so what's going to be the effect of having these two different overlapping fields? If you remember what I said, you can't let field lines actually overlap. So here I have field lines in opposite directions. And as you know, opposites attract. Here I have field lines in the same direction. And we know that the same fields repel. So what will happen is this object will be repelled from the top and attracted at the bottom. So what we get is a force acting on this wire, pushing it down. Now in your exam, you're going to be given lots of cases like that, where they will give you a pair of magnets, or north and south poles, and you will be asked to work out the direction of the force on something. So that can be quite tricky. So there's a really cool rule that you can use to understand that, and it's called Fleming's left hand rule. So you have to remember, it's the right hand grip rule for working out the direction of a field from a current. If you want to work out motion, or where something's going to feel a force, you use Fleming's left hand rule. So you take your left hand and you make this sign, the same sign as it's in here. So the way to think about it is you kind of make a gun, you lift your thumb up, so this is at 90 degrees, and then this finger here, you point inwards. Yeah? So you want 3 sets of 90 degrees, yeah, as if you're doing 3-dimensional coordinates. When you do that, what we can then say is that your thumb shows the direction of motion, or the direction that it's going to try to move in. In other words, your thumb is the force. Your first finger, that's showing the direction of the magnetic field. And your second finger shows the direction of current. So the current going from positive to negative. So this is quite tricky, and again, we'll do lots of practice with this in the lesson. But what you have to do is line up your hand so that the fingers are all in the right direction. Now we worked out earlier that current here is going into the page. So what you have to do is first of all line up your first finger so that it's in line with the magnetic field. So in this case, follow me through this at home, you need to make sure that your first finger is pointing left to right, because that's the direction north to south. It always has to point in the direction of the field. Now your second finger needs to be pointing into the page. So the trick to this is, I'm holding my finger like that, I'm pointing it at that wall over there. So all I have to remember is, all I can do is rotate my hand around while this finger keeps pointing in that direction. All I can do other than that is just rotate. So when I rotate so that now my second finger, my current finger, points straight down, now what I see, or down into the page, now what I see is that my thumb is pointing down the page. So my first finger's going left to right, my second finger is pointing into the page, and my thumb is pointing towards me, or to the bottom of the page. So that's the direction of the force. And you can do this in any situation where you want to work out where a magnetic field is causing a force. So let's just see that as an example here. For question 1, where is the force going to be? Well, I've got north to south. So I want my finger to be pointing north to south. And then I rotate it until my second finger is pointing up my page. When that happens, I can see that the force is going into the board. For question 2, I've got north to south again, but this time I rotate it so that my second finger is going down the paper. When my second finger is going down the paper, my thumb is going to point up out of the paper. So this one will come out of the page or the screen. Number 3, north to south. So I want this time to be pointing down my paper with my first finger. My second finger now points left to right. So my thumb is pointing straight up the page this time. So the force will go that way. Have a go at these other questions. When you come to here, these crosses, they are the magnetic field. So the crosses here means that the field is going into the page. The dots here means the field is coming out of the page. Have a go at the remaining ones. Okay, so let's go ahead and think now about a motor. So here's a motor, and this is the basic idea of it. What I have is a pair of brushes that are connected to a battery. So current comes from the positive end of the battery, through the brushes, through this bit that can turn, and then travels along through a set of wires like this, and then back out. And I've made it so that this is free to turn, so they can rotate around. Now what actually happens here? What I want you to imagine is, well, think about the south side. Think about it here. I've got current coming down the page, and I've got a field going from left to right. So using Fleming's left-hand rule, what direction will the force be in? Well, north to south. So my first finger points from north to south. My second finger, the current finger, is pointing down the page, and my thumb is pointing up. So the force is going to be acting up. What about on this side over here? Well, north to south. On this side, the current's going in the opposite direction. So now my thumb's pointing down, so it acts like that. And what I get is a pair of forces. Those two forces are going to turn, it's going to twist it around. So this motor is going to spin. At this end here, we have something called the commutator. The commutator is really important because imagine that the current's going this way. What will happen after half a turn? Well, if this part over here has travelled over to here, the current now would be trying to go in the opposite direction. So everything would be reversed, now the force would go up. I don't want that. I want something that will keep spinning round and round and round. So what the commutator has, can you see here there's a gap? So the idea is that this C-shaped part, that will rotate over so that it will end up on this side. And because this C-shaped part is attached to here, when it moves, the current in the coil will change direction. It will go from, so that whatever side of the coil is over here, so whatever side is on the right, will always get current going in. Yeah, current will always, current will always be coming out on this side, and it will always be coming in on this side. So inside the actual coil, the current will be reversing every half a turn. That's a little bit hard to see through just a video, so we will explain this a bit more in the lesson. You don't really need to know this for your course, but it's quite cool to think about it, and it just explains a little bit more about how this works. What I can say is that I know the direction of the force is there. There's an equation for the size of the force, and that is equal to this thing B, which is called the magnetic flux density. Magnetic flux density is a posh way of just saying how strong the magnetic field is. Stronger your magnetic field, the bigger B. It also depends on the current in the wire, so I get Li, and it depends on the length that is inside the magnetic field. So however much of the wire is inside the magnetic field gives you this idea L, and this tells us the force on the wire. So you can see straight away, if I want a motor to turn faster and with more force, then I can change one of three things. I can make my magnetic field stronger, I can make my current bigger, or I can have more length in my field. Now that could be just having physically a longer motor, or I could again put more coils in. If I put more turns in, more coils, each of those coils will have its own length, so it will get a very big force very quickly.